All right, good morning, everyone. Welcome back. Happy Monday. Only announcement is that the next Achieve will be posted later today or tomorrow. I'll try to get it up today, and that will be due next Monday. We've got about a month until the next assessment, so we have lots of time to learn. Yep. Clap. Now's the time to clap. I'm kidding. Okay, so at the end of class on Wednesday, we talked about these phase diagrams. So a phase diagram describes a pure substance. So water has its own phase diagram. Methanol has its own phase diagram. Any substance would have its own. And we ended with this iClicker where you were labeling different parts of this unlabeled diagram. So let's talk through those. So first is which phases are present in each area. And we can memorize where they are, but we can also think conceptually about what would happen if we had really low pressure and, low temperature and some pressure. Well, something that's really cold with some pressure on it will likely be a solid. So that's area C is solid. We have really low pressure and high temperatures. Those molecules would have a lot of energy. They'd be able to move around a lot. This is a gas phase. And then a mixture. So not super low temperature, not super low pressure. We have a liquid in between. So next is the line that represents where the solid and the gas phases are in equilibrium. And that's just the line where these two phases connect. So that's this line here, where we have kind of lower temperatures, lower pressures. Any temperature-pressure combination along this line, the solid and the gas phase would be in equilibrium. So I'll highlight this line here, and then just take a arrow to point to that. So that's where the solid and gas phases are in equilibrium. And then last, we're looking for the normal boiling point. Remember, a boiling point is where a liquid and gas are in equilibrium. If you're boiling a liquid, it's becoming a gas. The normal boiling point is that temperature that the liquid to gas equilibrium will occur at atmospheric pressure. Atmospheric pressure, we have units of atmospheres. 1 atmosphere is atmospheric pressure. So the normal boiling point, we go across this line at 1 atm and find where liquid and gas are in equilibrium. And that intersection there is the normal boiling point. So right here, normal boiling point is at 1 atm and where liquid and gas are in equilibrium. Now, I mentioned that different substances have different phase diagrams. That's because they have different boiling points, melting points, temperatures at which a solid, liquid, or gas would exist. On the next slide, I have 2 diagrams. One's for carbon dioxide and one is for water. Now, they look pretty similar except for where the boiling points are. At 1 atmosphere, if you look at carbon dioxide, at 1 atmosphere, it does not exist as a liquid. It only exists as a solid or gas, and that's why when you have dry ice, that's a solid carbon dioxide, and you bring it to room temperature, it evaporates from the solid. So sublimates is the word that we use there. You have to have a higher pressure and higher temperature for carbon dioxide to be a liquid. So again, these look pretty similar, but one key difference between water and carbon dioxide, which is really a key difference between water and most other substances, is the slope of this line between solid and liquid. For carbon dioxide, this line has a positive slope. Between the solid and liquid. So the slope is kind of to the right, which means that no matter what temperature, if you continue increasing the pressure more, then you're just going to have a solid. Liquid cannot exist if we imagine going a pressure that's way past where this diagram shows. At the high pressures, we'd have a solid. For water, that slope or that line has a negative slope. So that means if you're adding pressure, even with a low temperature, the solid will become a liquid. We won't have a solid necessarily for high pressures and low temperatures. So if we add pressure, the substance will become a liquid. And this is specific to water because liquid water is more dense than solid water. And that's because of the intermolecular forces that can exist between liquid water particles that can, and the liquid form can hold those water molecules closer together than can in the solid form. So there's more space between molecules in solid water than there are in liquid water. So solid water, ice, is less dense than liquid. You had a question up there? Good. So most substances we're just talking about slope of that line look like the carbon dioxide where it has a positive slope. Water is unique to most other substances because its solid is less dense than the liquid. All right, talk about this question with people around you. What would happen if we have a sample of H2O, let's say, not necessarily liquid, but sample of H2O at 5 atmospheres of pressure. It starts at negative 10 degrees Celsius and it goes to 350. What's going to happen with that sample in that process? All right, what phase is that sample starting off as? It's a solid. Yeah, I put some relative pressure and temperature values here. and then we have 5 atmospheres and -10 temperature, degrees Celsius. So that will start off as a solid, and then we're increasing temperature. So we start off as a solid, and then we're only increasing temperature. So we'd go across a horizontal line. The solid will melt or fuse, become a liquid. And then the liquid will evaporate or vaporize and become a gas. So all 3 phases can exist at 5 atmospheres of pressure, which depends on the temperature. All right. Questions about phase diagrams? Okay. Well, last term we talked about gases. So far this chapter we've talked a lot about liquids, and now we're going to talk about solids. So next unit we will just talk about different types of solids and their physical properties. So I've got a few pictures here of different types of solids. The first is chocolate. That's a mixture of different molecules, but that mixture is a solid. Its melting point is relatively low. If you're holding chocolate, that might melt in your hand. The next picture is salt. That's an ionic compound. We've learned about ionic compounds last term. Then we have metal. We have ibuprofen. This is another type of solid. This is graphite, which is what's used in pencils. Another type of solid. And these all have different properties because while they are all solids, their substances are different. So first we'll talk about molecular solids. So a classification of solids. These are solids that are made of molecules. Ibuprofen, this is a molecule of ibuprofen. So there's a bunch of carbon atoms, hydrogen atoms, and a couple of oxygen atoms that are all covalently bonded to each other in one molecule. There's much more than one molecule in one tablet of ibuprofen. There's many molecules. These are held together in the solid by intermolecular forces. So we've talked about with liquids. So these interact by intermolecular forces. We have ice at the top. Remember, ice is solid H2O. That's also a molecule held together by intermolecular forces. These melt or boil at relatively low temperatures. Compared to the forces that are holding other solids together, intermolecular forces are relatively weak. We'll talk about the other forces. So these melt and boil at relatively low temperatures. 1 unit of a molecular solid is 1 molecule. They're generally small molecules. So the unit of ibuprofen, if we're talking about 1 single ibuprofen or 1 single particle that still has the identity of ibuprofen, it's the molecule ibuprofen. So examples on the slide, we have ice, ibuprofen, carbon dioxide or dry ice as a solid. This is a molecular solid. There are plenty others, but we'll just list those 3 on this slide. All right. So molecular solids made of multiple molecules. Ionic solids are made of ions. So these interact by ionic bonds. Remember that ionic bond is the attraction of a negative ion, an anion, and a positive anion, or a cation. These melt or boil at relatively high temperatures. Ionic interactions are stronger than intermolecular forces. A unit is the ion, an ion. Examples here are ionic compounds. Sodium chloride, which is table salt, is sodium cation and chloride anion. Magnesium oxide is magnesium cation and oxygen anion. These are both ionic compounds held together by ionic forces between the cation and the anion, and have different properties because they're made up of different units. All right, so molecular solids, bunch of molecules held together by intermolecular forces. Ionic solid, bunch of ions held together by ionic bonds. Covalent network solids are atoms that are held together just by covalent bonds. So a diamond is an example of a covalent network solid, where the diamond is made up of only carbon, and they're held together, carbon atoms are held together by only covalent bonds. So these are all representing covalent bonds here. So these are atoms that interact by covalent bonds. These are strong interactions. Covalent bonds are strong interactions. Covalent network solids melt and boil at relatively very high temperatures. I don't know if you've ever kind of heard of melting a diamond. It can occur, but very high temps. And one unit we describe as these atoms covalently bonded throughout. Some examples here are diamond, which is just carbon in a specific bonding pattern. Carbon in a different bonding pattern is graphite. There are some double bonds in graphite. In diamond, there's all single bonds. Another example is silicon dioxide, SiO2. This is quartz. So have you heard of like quartz countertops? It's made of silicon dioxide. That's a covalent network solid. All right, next we have the last type, which are metallic solids. So these are solids that are made up of just metals. Please stop chatting, thank you. So these are solids that are made up of just metals, metal ions. These are metal atoms that are held together by delocalized valence electrons. So this image is to represent that there are metal atoms, positive because they have a proton nucleus. And these electrons are delocalized throughout. They can float around, interact with different nuclei. And as I was in high school, we learned this as an electron sea. This is also the language used in your book. So if you imagine a bunch of metal nuclei and core electrons in a sea of delocalized electrons. Those electrons can float around. These types of solids can conduct electricity because the electrons are delocalized. They melt and boil at a wide range of temperatures. So we can't categorize this into high or low. So we'll write low to very high temps. And then one unit we describe as metal atoms bonded by mobile valence electrons. Mobile, delocalized, is meant to communicate the same thing. I don't know if I've defined this in our class. Maybe I have, but I use this here. E, negative charge, and S to equal electrons. Just as shorthand. And examples are just different metals. So cesium, iron, tungsten, gold, silver, all of these exist as metallic solids. Checking, okay. Questions about these different types of solids? Okay. 4 different types. They're also summarized in a table in your book. So we're going to take different types of solids, or just solids in general, and describe them as a single unit, as a unit cell. So what we've described so far fall under the category of crystalline solids, or crystal solids. We'll use that term. And the unit cell is the simplest repeating units of a crystal. If we look at sodium chloride, there are sodium cations, chloride anions. We've seen this picture before. This is not one unit cell, this is many unit cells. A unit cell is a small portion of the crystalline solid that communicates the location and bonding of what is involved in that solid. So we have this defined on the next slide. So the unit cell is the simplest repeating units, or repeating unit of a crystal structure. In the previous slide, the picture of sodium chloride, there's a bunch of repeating units in that image. We see the pattern in that structure. So a unit cell is that repeating unit, that one unit that's repeated for that solid. There are 3 types. All 3 of them look the same right now. We're going to keep the first one as it is and then add atoms to the second and third. So let's talk about the first one first on the left. And so this we will call the simple cubic. Sometimes referred to as primitive unit cell. I'm going to flip back and forth between this slide and the next couple, the next one for simple cubic. So a simple cubic unit cell is a unit cell that has 8 atoms arranged in that cubic arrangement. So we've separated out the atoms, but if you go to the next slide, this is the simple cubic cell. This is many repeating units, but we have atoms stacked directly on top of one another and then a row like that in green. So one unit has 8 atoms, 4 on top. If we think about the 4 on top, 4 on the bottom, or you can think of 4 on the right, 4 on the left, same thing. But when we're talking about a unit cell, we're talking about what's within a cube. That cube is centered on those 8 atoms. And so you can ignore that. In one cube, at each corner, we have 1/8 of an atom. The rest of the atom is part of the cubic cell to the right, the cubic cell below, cubic cell in front, the cubic cell in front and to the right, the cubic cell in front and to the left for this bottom right corner. So there's, at each corner in a simple cubic cell, there's 1/8 of an atom. So in one simple cubic cell, there are 8 corners, and each corner has 1/8 of an atom. So if you add all of that together, we have 1 atom total per unit cell. And one other thing we'll describe for each type of unit cell is the length of the edge of the cube, an edge of the cube. For a simple cubic, the length of one edge, which is this length here, which is equivalent to any other length because it's a cube, all lengths, length, width, and height are equivalent. That length is equal to the radius of one atom plus the radius of another, so 2 times the radius. So we'll write that here. Length equals 2r, where this is the length, and r is radius. We'll write atomic radius. So we will do an example after we talk about these 3, where we use these formulas to calculate the density of a solid. So if you know what type of unit cell a solid exhibits, you can calculate its density. But we'll do that in a couple of slides. Okay, so this is the simplest one. The next one is called body-centered cubic. Or BCC, common abbreviation. In a body-centered cubic, we have the 8 atoms at 8 corners, and then in the space in the center of that cube, there's another atom. So centered in the body of the cube, we've got another atom. If you look ahead 2 slides, this is a body-centered cubic, and you can see now in the larger image, one atom is not directly stacked on top of another. There's an offset atom between the ones that are directly above. So in one unit cell, again, we have 1/8 of an atom at each corner, plus an entire atom in the middle. So per unit cell, there are 2 atoms. We have the 1 atom, which is the sum of all 8 corners, 1/8 of an atom at each corner, plus the atom in the center. So for body-centered cubic, we have 2 atoms per unit cell. And then the length of the edge of a body-centered cubic unit cell is influenced by that inclusion of that extra atom in the center. I'm not going to go into how this is derived. I'm asking you to trust me, but I believe that they're derived in your book. But the length of a body-centered cubic edge is 4r divided by the square root of 3. You can see on, if you go ahead 2 slides, that there's a greater distance between the atoms in the corners because of the space that the center one takes up. Here we're exaggerating the distance, but if you go ahead 2 slides, that is a better representation of the atoms. But see the atoms at the corners, now there's space between them, so the length is a little bit larger. Okay, so we've got simple cubic, body-centered with an extra atom in the middle, and then we have face-centered cubic. Or FCC. In a face-centered cubic, if you think about the outside of the cube. So the right side, the bottom, the top, the left side, the front, and the back. Those each are a face. That's the word to describe that. And so on each face, for a face-centered cubic, there is another atom. So what I'm drawing first is the atom on the right face. Then here's atom on the left, atom on the bottom, atom on the top, and then atom in the back. It's hard to see in that image, but skipping ahead to this slide, this is probably the best representation. We can look at this one as well. Let's look at this one first. So at the corner, same thing. We have 1/8 of an atom at each corner. And then at the face, there's another atom. But this atom at the face is shared between the cubic cell that this is representing and the cubic cell in front. So for every face-centered atom, only half of it is part of a unit cell. The other half is part of the adjacent cell. Okay, so we've got 1/8 of an atom at each corner. Then at each face, we have half of an atom. There are 8 corners, so 1/8 times 8 corners is 1. That's what we have for the primitive cubic cell. Then we have 6 faces, but half of an atom at each face. So that's 4 total atoms. 3 more atoms, 4 total for the unit cell. The edge length here is square root of 8 times r. Okay. So different solids can have different unit cells, simple cubic, body-centered, or face-centered cubic. When we do problems related to the unit cell, we'll be looking at a pure substance, so one atom that's in a specific shape. But if we think about ionic compounds, like sodium chloride, cations are smaller than anions. In sodium chloride, the smaller cations fill in spaces between the anions. Just looking at chlorine here, this is a face-centered cubic for chlorine. It's got 1/8 of an atom at each corner and half on a face. But the sodium atoms fill in those empty spaces between the anions. But most cubic cells that we will study will be for a single element. So in this case, sodium would have its own cubic cell and chlorine would have its own. This is the cubic cell for chlorine. Or we could add what's present for each sodium as well to discuss how many atoms are present in a cubic cell. But we'll just talk about individual atoms. So we will do this learning check. We are only going to calculate A, but I'll explain how to do B. I'll just cross it out for now. And that's something we can do in recitation. It's a similar process, but let's focus on A. So we're looking at copper. Copper atoms, they have an atomic radius of 128 picometers. We are calculating the density of copper consisting of simple unit cells. So the primitive unit cell. Okay, so what the heck do we do? Well, we're looking for density. Remember that density, Greek letter rho, is mass over volume. Mass is grams of copper. And we're looking at the density of a unit cell, so we need to find grams of copper per unit cell. And then volume is centimeters cubed. Which will be the edge length cubed for the unit cell. So we can find the mass, we'll get there. We can find the volume using that formula of the edge length for a simple cubic cell. Let's do mass first. So part 1, we'll be calculating mass. We need to find the mass of copper present in one unit cell. Going back to the slide where we described all of these, we know in the simple cubic cell, there is 1 atom per unit cell. So we'll use that to then get to grams. So let's start with 1 atom per unit cell. And then discuss with people around you, how can we then go from 1 atom per unit cell to the mass of copper in the unit cell? All right, what are your ideas? Over here? Well, you need molar mass of copper, so we'll go from moles to grams, but how do we get to moles? Avogadro's number, yes. We have 1 atom per unit cell. In 1 mole, there are 6.02 times 10 to the 23rd atoms. That's Avogadro's number. And then from moles of copper, we can convert to grams of copper. You sure?
I just thought it was just specific for gas.
Oh no, it's for any substance. All right, 1 atom per unit cell. Then in 1 mole, we have 6.022 times 10 to the 23rd atoms. And then for 1 mole of copper, if you look at the periodic table, its molar mass is 63.546 grams. So for 1 unit cell of copper, it weighs 1.055 times 10 to the negative 22nd grams. All right, so we've got mass, we've got grams, that's the first part of density. We need to continue and find the volume of a unit cell, which I said we can use the edge length cubed to find the volume. The edge length is 2r. R is radius. They tell us radius 128 picometers. Density units are grams per centimeter cubed. So instead of getting our final answer in picometers cubed and then converting to centimeters cubed, I'm going to go ahead and convert radius to centimeters now, and then we'll plug that unit, centimeters, into the equation. So first, radius picometers to centimeters. Radius is 128 picometers. Now, in the table that we learned last term, one of the units to remember is picometers to meters and centimeters to meters. But going from picometers directly to centimeters, I wouldn't necessarily expect you all to remember. So if you're working on homework, you can do a more direct unit conversion, but I will go picometers to meters. So in 1 meter, we have 10 to the 12 picometers. And then in 1 meter, we have 100 centimeters. You can certainly do a more direct one conversion, but just to demonstrate, that's the simpler conversion. So we've canceled out picometers, canceled out meters. We have centimeters. This is 2.56 times 10 to the negative 8 centimeters. Edge length for a simple cubic cell is 2r. So this is 2 times our value for radius. Oops. Oh, I wrote that down wrong, sorry. The radius is not 2.56. It is 1.28 times 10 to the negative 8. Then 2 times the radius is 2.56. Yeah. Oh, no, because we'll use L cubed for the volume, which is the length times the width times the height. And so L is just one edge. So we're looking for the length of one edge, not all of them added together. All right, so we have edge length. Now volume is edge length cubed, so 2.56 times 10 to the negative 8 centimeters, all of that cubed. And that value is 1.68 times 10 to the negative 23 centimeters cubed. So we have mass in grams, we have volume in centimeters cubed. To find the density, we need to just do that fraction. So density is mass over volume, 1.055 times 10 to the negative 22nd grams, divided by 1.68 times 10 to the negative 23rd centimeters cubed. This fraction is equal to 6.29 grams per centimeter cubed as the density for copper in a simple cubic cell. If we were to do part B, we'd have a different mass and a different volume. We have a different mass because in a face-centered cubic, there are 4 atoms per unit cell. So instead of 1 atom per unit cell, we have 4 atoms per unit cell. Then we'd have a different volume because the edge length has a different formula as well. So you would calculate mass using 4 atoms per unit cell, volume using the edge length for face-centered cubic, square root of 8 times radius. Then you'll have a different density. Questions on this problem here? seems like a lot, but I think if you break it down into these individual steps, it is more manageable. Okay, I'll give you all a second to digest, but we're going to start chapter 13. I've got like one slide to fill out and then the iClicker for today. So we will get to that in a moment. Oops. All right. So chapter 12, what we just finished, was all about pure substances. So pure liquids and pure solids. Chapter 13 is about solutions. So now we're mixing substances together, may not result or doesn't result in a pure substance. It will be a mixture or a solution. So we'll talk about the solution process, how you create a solution, and energetics of that. Different types of solutions, saturated, unsaturated, and supersaturated. When you have something dissolved in something else, you can communicate how much is there based on concentration. So we'll talk about different concentration units. You might remember molarity. We'll talk about that and a few others. And then different properties of solutions with ions and without ions. So that's an overview of the chapter. We're just going to start 13.1, the solution process. And to talk about solutions, there's some lingo that we need to discuss. So a solution, that's that first blank here, is a homogeneous mixture of two or more substances. So it is made up of more than one substance mixed together so that we cannot perceive the difference between the substances. It looks like one, which means that what is dissolved in the solvent, so we'll talk about the solvent in a second, is evenly distributed throughout. So it appears as one, but it's actually a mixture solution. The solvent is typically the component present in the greatest amount. This is what other particles are dissolved in, so it's dissolved in the solvent. We can have solid solutions, gaseous solutions, and liquid solutions. You could also have a solid dissolved in a liquid or a gas dissolved in a liquid, or you could have a solid dissolved in a solid and a gas dissolved in a gas. But the solvent will determine the state of the solution. So if the solvent is a liquid, the solution will be a liquid. If the solvent is a solid, the solution will be a solid. The solute is a component that's not the solvent. So what is dissolved in the solvent? Usually in smaller concentrations, that is the solute. So solutions, like I said, can be gaseous, liquid, or solid. So that is similar to what your question is on iClicker now. So I'll get this open. So you have 3 questions, 3 different types of solution, or 3 different solutions, and you are identifying either the solvent or the solute. Read the question carefully so you know what you're looking for. There is a solid solution, a liquid solution, and a gaseous solution. And so you're just trying to select what the solute or the solvent is in those 3 examples. Yeah, that's common. I've seen that with other students with all the teachers that are. I think it's just a lot of All right, this is the last thing we'll do today. So we'll discuss the iClickers on Wednesday. I'll leave this open for a few more minutes here.